Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library, and I have a great story to tell you. Tonight, we're going to explore the inside of our planet. Similar to our journeys in space, we will gradually descend towards the Earth's core and discover what lies beneath our feet. To begin with, I will discuss various phenomena happening on the surface, such as continental drift and volcanism. Then we will explore the various layers existing between us and the center of our planet. As always, we will keep things very simple and easy to understand, even for those with no scientific background. I will explain how the Earth's core shields us from solar radiation and how the Earth is slowly cooling down. Additionally, I will delve into how humanity, across diverse civilizations and centuries, has imagined or theorized what our planet is composed of. Our ancestors were very creative. They envisioned different possible forms for the world: flat, hollow, with passages to various underworlds. And we will explore the origins of these visions and how they survived in popular culture across novels and fiction. But first, I would like to take a few seconds of your time to let you know that we have a Patreon page for those of you who wish to and can support this project, get more of it, and listen ad-free on their favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially, and this really keeps us going. If you join, you will gain access to various new features. For example, you will have the option to listen to all episodes with or without background sounds and receive regular bonus episodes. We already offer several exclusive episodes to our Patreons. The latest one is a very interesting story about the history of mirrors. In addition, you will also be able to download all these audios to listen to them offline and participate in selecting future topics. We also offer advanced releases and updates on upcoming episodes. We hope to see you there soon so that we can continue developing Lights Out Library, which we thoroughly enjoy. You will find a link in the description box and the first comment pinned under the video. As always, you do not need to watch the video to follow along. If you fall asleep and wish to resume the video later or jump directly to a particular part of the story, timestamps are also listed in the description and pinned in the first comment, as well as links to different streaming options like Spotify, Apple Podcasts, and Amazon Music, which may be better suited for you. But before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries as we embark on this adventure together. Now, assume a comfortable position. Maybe move a little bit to settle. Take a long, deep, relaxing breath, and when you slowly exhale, feel your shoulders drop, release the tension in your neck. Let your face soften and your jaw to relax, and make sure your fingers are not clenched, and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. We have a lot to discover tonight, so keep your mind open and peaceful. Our descent begins right now. We're going to begin our story in Russia, more precisely in the Kola Peninsula near Finland. Why there? Because over a period of more than 20 years, the Soviet Union drilled in this region the deepest vertical hole ever in the Earth's crust. This was not done to search for oil or other resources, but as a research and engineering project to study depth drilling, geophysical phenomena, and the nature of the rock layers. The hole is very narrow, only 23 centimeters wide, about 9 inches, but it is 12 kilometers deep, or 7.5 miles. To this day, it remains the deepest artificial point on Earth. Even though there are a few oil wells drilled in the past few years that are almost as deep. Now, 12 kilometers deep is just a little scratch on the planet. But at the scale of the Earth's crust, it is significant. In the Kola Peninsula, the crust is estimated to be 35 kilometers thick, or 22 miles. At this depth, representing about a third of the crust, the temperature at the bottom of the hole is already 180 degrees Celsius, 350 degrees Fahrenheit. This high temperature made drilling unfeasible, which is why it stopped in 1992. The more we descend underground, inside the Earth, the more the temperature rises. This is just the beginning because when we reach the core of our planet, we will find temperatures that are much higher, similar to the surface of the sun. But why is the Earth so hot? To understand this, we need to go back several billion years in the past and look at how our planet was formed. According to current theories about the formation of the solar system, Earth and all the planets orbiting the Sun appeared in the early ages of the system. A star forms when a large quantity of matter gathers and starts accreting because of gravitation. An accretion disk made of dust and gas takes shape and progressively, over millions and millions of years, gives birth to one or several stars at the center. In the case of the solar system, most of the matter went into the formation of the sun, about 99% of it. The rest stayed in orbit around the sun and formed the planets and other smaller bodies. Many kinds of planets appeared in the solar system. Gas planets like Jupiter or Saturn probably have a solid core, but are mainly made of gas, hydrogen for the most part, and this gas is kept together by gravitation. There are also rocky planets that are solid and have a well-defined surface. There are 4 of them in the solar system: Earth, the biggest one, and also Venus, Mars, and Mercury. Additionally, there are many more smaller bodies that are not considered planets because they are not as big, but have a similar history. These include dwarf planets like Pluto or Ceres, satellites like the Moon, and millions of smaller asteroids. Rocky planets appeared by absorbing most of the matter on their orbit. They cleared space of matter bit by bit after tens of millions of years of collisions with increasingly larger asteroids. As the dust progressively concentrated in the solar system, in the case of the Earth, it is believed that 2 protoplanets formed on a similar orbit. They finally collided in a very violent shock, and this is how the Earth almost reached its current mass. However, in the shock, a lot of matter was ejected into space, and this matter would have formed the Moon. Above a certain mass, rocky bodies take a round shape because of gravitation. There are plenty of asteroids that are not spherical because they are not big enough. There is not enough mass for gravitation to shape them into a round form. So, from the moment it appeared and took shape, the Earth was intensely hot as a result of its formation. Larger and larger objects collided with it, and their speed, or their kinetic energy to use the scientific term, turned into heat. Additionally, the Earth is hot also because a lot of heat keeps being produced inside by nuclear decay. The Earth contains radioactive materials like uranium that it received during its formation. And long after the planet was formed, this material continued to release particles and generate heat. In the case of Earth, it is estimated that about 20% of its internal heat comes from residual energy from the accretion process. All these collisions that formed the planet. However, for the most part, the remaining 80% of its heat comes from radioactive elements that continue to decay, much like a nuclear reactor. Over time, a rocky planet cools down, starting from its surface. The heat dissipates into space, and the radioactive elements inside gradually disappear as they disintegrate. This process can last billions of years. It is very slow. But this is how the external layer progressively transforms from liquid rock into a solid crust, which tends to become thicker and thicker as the planet ages. For example, in the case of Earth, it is estimated that heat production inside the planet 3 billion years ago was twice what it is now. The formation of the planet and the laws of physics also explain its internal structure. Once a planet is formed, the various elements it contains tend to migrate within it. Together with different levels of pressure and heat, this migration creates differentiation between various layers. Beneath the Earth's crust, we find different layers that have distinct characteristics, compositions, elements, temperatures. But as we journey from the surface toward the center, let us begin with the crust. This solid layer where life appeared and one which we live is not even everywhere. In some places, deep under the ocean, it is only 6 kilometers thick, less than 4 miles. While in mountain chains, for example, it can be up to 50 kilometers, or 30 miles thick. The crust is mainly composed of rock, which we will examine later. However, as anyone who has experienced an earthquake or witnessed a volcanic eruption knows, the crust is not perfectly still and stable. The main theory today that explains the motion and activity of the crust on a global level is called plate tectonics. It has been accepted by the scientific community since the 1950s and 1960s. and little doubt remains about its validity because it explains several phenomena very well. These include the presence of the same geological layers on different continents and the presence of similar species. It also accounts for seismic activity, the formation of oceans and mountain chains, and what we know about the internal structure of the planet. What plate tectonics says is that even though the Earth's crust is mainly rigid, the crust and a small layer just under it are broken into different plates that can move. They move extremely slowly, generally by just inches every year. But when you multiply this by hundreds of millions of years, the face of the planet, with the location of continents and oceans, can change completely. Why do these plates move at all? Because there is motion underneath the inner layers of the planet that we will explore later. Another explanation for the movement is the pull, also known as the tidal force, from the moon and the sun. It isn't clear and remains a subject of debate, but various forces combined put plates in motion. When these plates meet, their thickness and relative motion determine the kind of boundary between them. One plate can slip under another and push it up. This is how the formation of the Andes and the Himalayan mountains are explained. In the case of the Andes, there is a medium-sized plate that is almost entirely underwater, the Nazca Plate, which passes under the South American plate and compresses it on its western fringe, making and continue to make the Andes rise. In the Himalayan mountains, it is a subduction of the Indian Plate that lifts the Eurasian Plate. Not all plates collide frontally, depending on their motion. They can also rub against one another or diverge. There are rifts where new material surfaces and pushes in opposite directions. The largest rift on Earth is in the center of the Atlantic Ocean. Hundreds of millions of years ago, Europe, Africa, North America, and South America were all parts of the same landmass. The rift that became the Atlantic Ocean opened and pushed the continents apart, where the planets meet. The forces at play are enormous. Most of the time, nothing happens, and tension may accumulate inside the rocky layers. They don't move despite the push they are subjected to. But suddenly, sometimes after years or even decades, this energy can be released at once. The plates move up several meters relative to one another, and there's an earthquake. Depending on its depth, the type of rocks, and the directions of the force at play, it can be more or less destructive at the surface. Because the shock waves may travel inside the crust, a shake can happen theoretically anywhere. However, the most violent and frequent ones occur near plate boundaries. If you live in the middle of a large continental plate, like east of the Rocky Mountains or east of the Andes, or in most of Europe, you are unlikely to experience a powerful earthquake. But if you are near a plate boundary, earthquakes and volcanic activity are much more common. The most active seismic and volcanic regions of the world are located around the Pacific Ocean, in a vast region shaped like a horseshoe, almost around the east of Asia and the west of the Americas. About 3/4 of active volcanoes in the world, and by far the biggest earthquakes happen in that region. Bit by bit, the Pacific Ocean is shrinking. It's very slow, only 1 inch per year. But even though it will take hundreds of millions of years, the Pacific's days are actually numbered. Meanwhile, the Atlantic Ocean is expanding thanks to its rift. One day, Asia and America will collide and form a single continent, as they did in the past. There was a time when all of the Earth's landmass formed one single continent, the continent called Pangaea. It is believed that plate tectonics appeared only 3 to 3.5 billion years ago, when the Earth had cooled down enough for rigid plates to appear on its surface. As Earth keeps aging and gets colder, as it loses heat and produces less of it because its stock of internal fissile material decreases, plate tectonics will also end one day. The crust will form one single thick plate, and its surface will stop changing shape. It is believed that on other smaller planets like Mars, this already happened. Like Earth, Mars has a differentiated structure and formed through a similar process of aggregation. But it has already cooled down more since it's a smaller planet. There would no longer be plate tectonics on Mars. A consequence of plate tectonics, with new material appearing in rifts and older material melting again when it is subdued under a plate, is that the material on the surface of the Earth is much younger than the planet itself. Oceanic floors are only 200 million years old on average, whereas a planet is several billion years old. The oldest layers of rock in the crust are about 3 billion years old and are found in continental regions in the middle of large plates, like in Central Asia. In any case, looking at tectonic plates makes the map of Earth look very different. The largest plates are the Pacific Plate, which occupies a big part of the Pacific Ocean, and the Eurasian Plate, which contains most of Asia and Europe, with the notable exception of India. There is the African Plate too, the North American Plate, and also much smaller plates like the Caribbean or the Arabian ones. Now, plate tectonics as a theory is less than a century old. Before its development, mankind had various and very different visions or explanations of natural phenomena like earthquakes, and more generally the shape of the Earth and what it was made of. The majority of ancient civilizations that left documents pictured the world as flat, which is logical because this is how we perceive it. For ancient Egyptians or Mesopotamians, the world was supposed to be a disk floating in the ocean, and the sky was a dome, with the moon, the sun, and stars embedded in it. Greek philosophers are generally credited with theorizing around Earth, and they did. But among many other theories, some of them thought that the Earth was a short cylinder or that it was a dish riding on air. In Europe, the ancient Norse and Germanic people, also believed in a flat Earth, with the Earth surrounded by an ocean and a central pillar, or the world tree, in the center. The same was true in China, except the Earth was pictured as square, whereas the heavens were round. This assumption remained unquestioned for a very long time in China until the 17th century, with the introduction of European astronomy in the country. In ancient India, text pictured the Earth as flattish. It is just one of a stack of flat disks, each of them representing a different world. From the 5th or 4th centuries BC, the view that the Earth was round gained traction in ancient Greece and among Indian astronomers as well. By the time of the Roman Empire, it had become a mainstream view among scholars because, in fact, the general population was not educated and probably didn't even wonder what shape the world could have. This vision remained until the early medieval period and was also adopted by Islamic scholars. There was a significant development of astronomy and mathematics in the 8th and 9th centuries in the Middle East, allowing the calculation of the movement of planets. Islamic scholars were aware that the sun rises at different times in various parts of the planet, and there was apparently no dissent among them regarding the round Earth theory. Various Muslim scholars explained that the Earth looked flat because it was so big that its curvature was not visible to a single person. That was a good explanation. But one point that remained to be explained was how people living in the southern hemisphere didn't fall. There was no understanding of gravity, or that we call up and down is a product of our perception. What we call down is actually the direction towards the center of the Earth, the direction of the gravitational force that keeps us stuck to the ground, and this issue remained unsolved for centuries. Contrary to what people sometimes suppose, in medieval Europe during the Middle Ages, the Earth was also seen as round, at least in universities and official teachings. The vision enforced by the Church, in particular, was that the Earth was round, but also that it was at the center of the universe. It was because of this debate regarding the position of the Earth relative to the Sun especially, that astronomers like Copernicus and Galileo were condemned by the Church, as they insisted on putting the Sun at the center. Now, common people may have assumed during this period that the Earth was flat, based on their sensory experience. Even educated navigators were not perfectly comfortable with the round Earth theory. For example, the Portuguese, who were the first European navigators to explore south along the coasts of Africa in the 14th and 15th centuries, were nervous that the ocean might end and that their ships could fall into a void eventually. But finally, they pushed even further to the south, and in the 1400s, their navigation confirmed that the ocean never ended abruptly. In the 16th century, the first trip around the world was made by the Magellan expedition. From this moment on, the various hypotheses of the Earth being something other than round were mostly eliminated. Another vision that appeared long ago and lasted longer was the hypothesis that the Earth was round but hollow, or that it contained an interior space with an entirely different world. This concept of subterranean land inside the earth appeared in various mythologies. In Greece, there was an underworld where souls were supposed to go after death. There was ambiguity in Greek mythology about whether it was a real place with an entrance from the physical world or just another dimension only accessible to spirits. There were similar underground worlds in Norse mythology or in Tibetan Buddhism. This is also the kind of representation of hell that existed in the Christian and Jewish traditions. In various mythologies, there were legends about the actual entrance to the underworld. For example, in Ireland, there is an archaeological site called the Rathgrogan. According to legend, there was a cave on this site from which creatures from the underworld emerged. Also in Ireland, there is an island called Station Island, an ancient pilgrimage site where a cave supposedly communicated with the inside of the earth. There is a chapel built on the cave, and it has been closed since the 17th century. There are many more examples of legends and traditions about an underworld in the Hindu mythology, Native American legends, or in Russia about the Samoyeds. The Samoyeds are a Siberian tribe living north of Siberia in a very harsh environment. According to a Russian legend, the Samoyeds traveled to a cavern city to live inside the earth. Sometimes this underworld could be hell. It could be a refuge where people found shelter or a new land. Or it could be the place from which tribes or people came from. But in the 16th and 17th centuries, when the round earth theory was replacing for good other visions of the world, the hollow earth hypotheses resisted in Europe, including on scientific grounds as an explanation of certain phenomena. One proponent of this idea was Edmund Halley, an English astronomer and an important and serious one. Halley's comet is named after him. He computed the comet's periodicity among other works. At the end of the 17th century, he put forth the idea of Earth being like a hollow shell with two inner concentric shells, and after all that, the core at the center. He supposed these different spheres had their own magnetic poles. I will tell you about magnetism a bit later. He also supposed that they rotated at different speeds. That could have explained anomalous compass readings, and maybe even the aurora borealis. He supposed the aurora borealis could be gas escaping from the space between our sphere and the one below. There were other tentative descriptions of the inside of the Earth in the 18th century and early 19th centuries, sometimes including an internal sun at the center of the Earth. Bit by bit, in the 19th and early 20th centuries, these ideas exited scientific circles because of the understanding of the Earth's mass, new hypotheses about the formation of planets, and better observation of other planets. All of this made the descriptions of the hollow Earth, and sometimes the idea of people who would have lived under our feet, less credible, and completely unsubstantiated in any case, which meant they couldn't be a part of the scientific field. When it became possible to test the ground with seismic waves, when the theory of relativity defined what gravity was, or when holes were drilled several kilometers into the ground, like the Kola superdeep borehole when we started, the hollow earth hypothesis died. It died as a scientific conjecture, but in the meantime, it had started a successful career in fiction. Already in 1741, in the 18th century, there was a fictional novel by Ludvig Holberg, a Norwegian writer, about a character who fell through a cave and lived several years on a smaller globe inside the shell on which we live. The concept of a hollow earth appeared in various forms in many 19th century novels, including those by high-profile and successful writers like Edgar Allan Poe and Jules Verne. One of the most famous novels featuring another world inside the Earth is Journey to the Center of the Earth by Jules Verne. It describes a prehistoric subterranean world explored by an expedition that found a passage under a volcano in Iceland. The popularity of this concept in fiction has not decreased, perhaps because it has become really hard to imagine lost worlds on the surface of the planet, now that the world has been entirely explored and mapped. But under our feet? Why not? It's a fun idea, at least. Apart from a hollow world with different spheres inside, like Russian dolls, another conjecture, though even harder to believe, was actually clever when you think about it. It suggested that we could live not on the outside of a bowl or sphere, but on the inside, walking on its internal wall. In this vision, we call space, the sun, planets, stars, would be inside the sphere. This idea is clever because, even though it doesn't align with what we know about distances, the size of the sun, or the universe in general, it could explain many things back then. First, it could account for the fact that it never ends when you travel on Earth. There is no edge to it. If this is not the outer surface of a sphere, then it has to be the inner surface. Additionally, it could explain gravity through centrifugal force. However, our knowledge of what lies beneath our feet, beyond just a few miles of crust, truly developed later in the 20th century. This advancement came with models of planetary formation and significant leaps forward in geology, facilitated by new techniques, such as the use of waves that travel across layers of rock. These waves can relay information about what the layers are made of based on their speed and the direction in which they propagate. Now that we have examined the first few miles of the Earth's surface, it is time to start our descent towards the Earth's core. There is a boundary between the crust and the region underneath, called the mantle. This boundary is known as the moho and is about 500 meters thick. It is where the composition of the Earth changes. In the crust, the most abundant element is silica, or silicon dioxide, which we generally call sand, as it is its main component. There is a profusion of different types of sand, but silicon dioxide makes up to 50 to 60% of the crust. Another major component, accounting for about 15% of the crust, is aluminum oxide or alumina. There are also plenty of other oxidized components, including calcium, magnesium, and iron. Oxidize means that the basic elements like silicon, aluminum, or iron are associated with oxygen. Basic elements do not come in pure forms in nature. On a rocky planet like Earth, they have a high propensity to form molecules with oxygen. In fact, oxygen is probably more abundant on Earth than you might think. Looking at the entire planet now, not just the crust, it is estimated that oxygen represents about 30% of it, almost one-third. The only element that is more abundant in the entire Earth is iron. Iron constitutes about 30 to 33% of Earth. Among other elements, silicium is about 15% of the planet and magnesium is 14%. This makes the Earth very different in its composition from the rest of the solar system. It is not that different from other rocky planets, but the main components of the Sun and gas giants are hydrogen and helium, whereas these elements are marginal on Earth. They're not absent either. There is hydrogen wherever there is water, but at the scale of the planet, hydrogen represents less than 1% of the total mass. The nature of the elements under the crust is very different from what we find in our biosphere at the very surface. The reason why the planet is not homogeneous, the reason why its various layers are made of different elements, is the differentiation phenomenon mentioned earlier. When rocky planets form, the heavier, more massive elements tend to migrate towards the center, towards the core. For that reason, the Earth's core is estimated to be made of 90% iron and 6% nickel, more massive elements. We will see later that this is very important for life on the entire planet. This differentiation happens on every rocky body of a sufficient size. The heat inside a planet maintains it in a liquid state, so that denser materials tend to fall to the center, whereas lighter elements migrate toward the surface. The differentiation never reaches 100%. This is why there is iron in the crust too. And it didn't entirely join the core. But as a rule, the more we descend towards the center of the Earth, the more we will encounter heavier elements such as metals. In the mantle, which we are now entering as we pass this boundary called the borehole, the chemical composition suddenly changes under the crust. We are going to discover a completely different environment. The mantle makes up 2/3 of the Earth's mass and more than 80% of its volume. It is the bulk of our planet in geological terms. Just under the crust, the temperature is around 200 degrees Celsius. That's 400 degrees Fahrenheit, which is not that hot yet. This is the temperature of a kitchen oven. But at 3,000 kilometers down, near the core, the temperature reaches 4,000 degrees in the lowest layers of the mantle. 4,000 degrees is hard to describe. It is still relatively cold compared with temperatures inside the sun, for example, but it is sufficient to melt any man-made material. The most resistant, high-performance ceramics used in the latest generation nuclear reactors to stop the reactor core from melting can withstand temperatures up to 2,000 degrees. And the temperature at the lower level of the mantle is twice as high. At this temperature, any rock would immediately melt. But this doesn't mean the mantle is liquid. It is actually rather solid because something compensates for the heat, the pressure. Generally, a rise in temperature tends to turn material from solid to liquid and then to gas. But pressure has the opposite effect. The rise in pressure forces materials to remain solid. We have all seen very liquid lava coming out of a volcano. It is liquid because it's hot, but also because the pressure at the surface allows the rock to be liquid. The same lava material, when it was inside the mantle before rising to the surface, was much more solid and viscous due to the pressure. This enormous pressure, which is called lithostatic pressure, increases as you descend inside the mantle, and it counterbalances the heat to keep everything mostly solid. Mostly because it's not perfectly still. The upper layers of the mantle are liquid enough to allow tectonic plates to move, and the matter in the mantle also moves. Things can move because rocks at such high pressure are still able to very slowly deform, and because the center of the Earth is very hot, whereas the crust and the upper mantle are comparatively rather cold. This creates convection movements inside the mantle. This difference in temperature means that hotter material tends to rise towards the surface, while cooler material tends to sink. This colder material largely comes from the subduction between tectonic plates. When one plate passes under another, its material descends into the mantle and it's progressively absorbed by it. This process creates movements in this high-pressure, high-temperature environment. Meanwhile, there is a rift between two plates and a new floor appears. The material comes from the mantle. It is a very slow process, but there is this constant exchange movement between the mantle and the crust. And sometimes these processes can be responsible for the presence of heavy materials close to the surface. For example, almost half of the accessible copper reserves in the world are located in Chile and Peru, near the Andes. This is not a coincidence. These resources have been lifted close to the surface by convection in the mantle and tectonics. The mantle is also divided into various layers with different properties and different viscosities. It is not homogeneous at all. Some parts are more viscous than others, but what we know about it is mainly based on theories. The main observations that can be made are with seismic waves that are sent through the mantle. It is possible to guess what a layer is made of by studying how waves cross it, at what speed, and how they are deflected. However, exploring the mantle with a probe is extremely difficult because of the depth, heat, and pressure. There have been attempts to collect samples from the mantle or close to it by drilling on the seafloor where the crust is thinner. But these experiments have just scratched the surface and not reached further than the lowest levels of the crust. The various layers of the mantle end about 3,000 kilometers, or approximately 1,800 miles, under the surface. Below this begins the core, which is not homogeneous either. There are two main regions of the core. First, there is a region called the outer core, where the temperature rises again up to almost 8,000 degrees. Consequently, so does the pressure, but not enough to keep the outer core solid. It is believed to be liquid and, contrary to the mantle, It is no longer mainly rock, but metal this time: iron, nickel, and maybe traces of sulfur and oxygen. At the bottom of the outer core begins the inner core, which is our final destination, as it is the innermost layer of the Earth. There is a lot to say about this system with the liquid and solid core. There is no direct evidence about the composition of the core. All we know about it comes from information given when seismic waves cross it and current theories about the formation of the Earth. The inner core is distinguished from the outer core, even though they have about the same composition, mainly iron. This is because the inner core becomes solid again. Pressure keeps increasing and it counterbalances temperatures at this depth. And we can figure out the inner core as a metal bowl floating in the middle of a liquid metal ocean. It seems that the solid core is growing slightly at the expense of the liquid part. This is because the planet keeps cooling down. There is a bit less heat year after year, but pressure remains the same. The part that is solid, the inner core, tends to grow at the expense of the liquid part. It is very slow, only 1 millimeter per year. But in geologic times, this is significant. It means 1 meter every 1,000 years and 1 kilometer every million years. There are still several billion years to go at this rate before the liquid core disappears. But this will eventually happen. The solidification of the entire core could have dramatic consequences for the entire planet, because the core probably moves differently from the rest of the planet, as it is liquid and is not directly attached to it. There is a theory that explains the existence of the Earth's magnetic field by the movement of the outer core. This is called the dynamo theory, and I'm going to explain what it's about. Astronomers and physicists detected the existence of a magnetic field around certain bodies, including Earth, quite a long time ago. So what is magnetic field exactly? You know, magnets pull some materials like metals and can repel other magnets, while the materials like glass or plastic, they seem to not react at all. This happens because of the movement of electrons. You know that atoms are made of a core with protons and neutrons, and around this core are electrons, which are smaller particles. These electrons can move and circulate between atoms, which is what happens in electricity. Electricity is a flow of electrons between 2 points. Certain materials, especially metals, are better at conducting electricity because their atomic structure allows their electrons to move easily and be separated from their atoms. When we use electricity, what we really do is create a bridge, a passage, between 2 points that have different potentials. One can release electrons, and the other one is electron hungry. We use this flow of electrons to make a motor work, to heat something, or to transmit information, in the case of electronics. Magnetism is another property related to electrons. Electrons are constantly moving, not only between atoms, but inside them too. They turn around the atom's core at high speeds, and even more importantly, they spin like a spinning top. This spinning creates a force that can attract other atoms and turn each atom into a tiny magnet. Most of the time, this pull, this attraction at the atomic level, doesn't extend to entire objects because atoms are pulled together a bit chaotically. They have different orientations, and they are not organized in an orderly manner, meaning that a little pull generated by each atom is compensated by others, and as a whole, the object does not act like a magnet. However, sometimes materials naturally have this property and are natural magnets, or they can acquire it when they conduct electricity. When they conduct electricity, their atoms get reorganized to pull in the same direction, and they become magnetic. For example, two wires conducting electricity in the same direction will attract each other, and they will repel each other if electricity moves in opposite directions. A few materials can have this property naturally, or they can acquire it when they are put in contact with another magnet that reorganizes the positioning of their atoms. These materials are called ferromagnetic materials, and they include elements like iron and nickel and alloys that contain them. This is typically how the magnet you may have on your fridge works. The area around such an object, where its attraction or repulsion is perceptible, is called the magnetic field. To obtain magnetic fields that are more powerful and can be used on demand, electromagnets have been created. They are used extensively in industry, and although you may not know it, you probably own several of them. They are used in motors, relays, loudspeakers, and hard drives. A typical electromagnet is made of a core of ferromagnetic material surrounded by a spiral of wire. Electricity through the wire creates a magnetic field around the system, and the field disappears when the current is turned off. What an electromagnet does is basically transform electricity into magnetic energy, into magnetism. I'm telling you all this because the entire planet we live on is surrounded by a giant magnetic field, and this magnetic field is a vital component of the equation that makes life as we know it viable on Earth. It shields the planet from radiation, from streams of particles emitted by the sun that would make at least human life unsustainable if they were to reach the surface. All around the planet, on the fringes of this magnetic field, there is a region of space of much higher radioactivity. It's called the Van Allen belt, where the Earth's magnetic field repels these particles. Since this magnetic field was discovered more than a century ago, the question of why and how it works has been a field of investigation for scientists. The main theory that explains it nowadays is the dynamo theory. There are various possible practical explanations for it, but the concept is that the Earth itself constantly generates this magnetic field by transforming the currents of electrically charged particles that circulate between the core and the mantle into a giant natural magnetic field. This is possible only because liquid iron in the outer core can move independently from the mantle. Similar magnetic fields exist around other planets with a partially liquid iron core, like Mercury. Mercury is a small planet that could have cooled down quickly and lost its liquid metal core long ago if it were further from the Sun. But Mercury's core remains very hot, not really because of the solar heat that Mercury receives, but because of the Sun's gravitational pull. Mercury has an elliptical orbit around the Sun. This means that the gravitational pull from the Sun can be stronger when Mercury is close to the star or weaker when it's farther. These variations in the gravitational pull provoke friction inside the planet. This is called tidal energy, and it keeps the core warmer. On the other hand, there are rocky planets with no dynamo effect and no magnetic field because they don't have enough of a magnetic core, or it is no longer liquid. That's the case of Mars. Mars has no magnetosphere like Earth. Mars has a light atmosphere that absorbs some of the solar radiation, but still, the radiation level on its surface is about 60 times what it is on Earth, and even 3 to 4 times what astronauts absorb when they are on board the International Space Station. This is one of the main challenges to colonizing Mars, and an element among others that makes it very hostile to human life. For the time being, the only options for humans to survive on Mars would be to live underground or under anti-radiation domes. So among all the elements that make life possible on our planet, including the atmosphere, liquid water, temperature, the presence of basic building blocks of organic compounds, and the distance to the Sun, there is also the very structure of the planet and the fact that its core is not welded to the mantle, which makes the generation of this magnetic field possible. We have now reached the end of our journey for tonight, and we now have to return to the surface. I hope you enjoyed this adventure, and I invite you to discover and learn more. Now you can let go and sleep. Or if you are not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.